Well, I'm rubber and you're glue, so everything is going to bounce off me and stick to you. So in this lesson, we're studying momentum. That's going to be momentum, things flying around, and collisions. Now we might have inelastic collisions, and this is where things would stick like glue. And over here we would have elastic collisions, where things would bounce like rubber. Momentum is relatively simple. It's essentially a vector, denoted as P. It's going to be mv, simple. Vector is going to be the velocity, mass is simply a number. So P equals mv. Alright, well, let's go over here. Let's imagine something flying this direction, a little ball here, and maybe another ball over here is flying this direction. And these guys are sticky balls, so once they collide together, they are going to stick. And, well, because this arrow is bigger and longer and more powerful, this side right here, it's going to sort of keep that force momentum continuing in this direction, so that's going to be essentially what's happening there. We can mathematically represent that as m1v1 plus m2v2 equals m1v m1 m2, both of these two things combined, m1 plus m2, and then the final velocity, this is the final velocity over here, m1v1 m2v2, the final velocity with both of them combined, m1 plus m2. That's an important factor when things stick together, that you add the masses together. This is going to be a recurring theme in other types of problems as well. Now let's look at the elastic collisions. This one is a simple one. It's very simple. The inelastic ones are easy. It's the elastic ones that get a little bit weird, because now all of a sudden you have to just memorize these big equations. Let's just go ahead and take a look at the resting target scenario. This would be if you have a ball and it's essentially just a little bouncy ball. This one is going to be hitting a resting target just like that with no velocity on the second one. So we would say V1, and this is the final V1. This is V1 over here, M1, good lord. We have M1, V1, and this is just M2, V2. Well, like you'd expect in this scenario, afterwards, this one would probably be moving a little bit in this direction, possibly, and then this one would be moving possibly in this direction. We don't really know, but this is going to be essentially V. We're trying to figure out here is V1 and V2. So we have V1 being this one. The first ball's velocity after it collides. It's simple. It's just going to be M1 minus M2 over M1 plus M2. Now the bottoms of all these, the denominators of all these different equations will be M1 plus M2. And at the end here, we always have a velocity. This is going to be V1 initial. Great. So for the second ball, V2F, that's going to be this ball right here. This is going to be 2M1 over M1 plus M2, V10. Alright, that's pretty easy. So this is essentially, unlike that line, this is essentially the resting situations. And over here, we're going to put the moving target. Alright, this is actually the one that is going to be at rest over here. The resting target. And this one was going to be the moving one, right? This is the one that moves, this is the one that rests, just so you kind of understand which ball is which. And over here, in the moving target situation, we could have very similar equations. So V2F, oh whoops, this is still V1F, my bad. V1F is equal to, essentially it's the same thing, right? Started it the exact same way, M1 minus M2 over M1 plus M2, and here's the V1. But then after that, you're just going to add plus 2M2. This is going to almost look like this. It almost looks like that, but it's different numbers. It's M1 plus M2, as usual, but then it's V2, 0. So in this case, we're starting to include what the second ball is doing. Notice in this first case, the second ball is doing nothing. This stuff just cancels out and becomes 0. Okay, in our equations, it's gone. But over here, we have to include it. So now, if this ball was moving, all of a sudden now there's going to be a second component to the equation. So that's just going to be V2F. This is the one that was, they're both moving now. This is the one that was previously at rest, and now they're both moving. So we start it the same way. We have 2M1, M1 plus M2, as usual, V1, 0. And then on this side, we're going to subtract what that ball sort of would look like, but it's on this side. So it's going to be like M1 minus M2, M1 plus M2, V20. So it turns out that at the end here, they both have V20, and on this side, they both have V10. This is essentially saying the initial of the ball 1, velocity 1 initial, and this is velocity 2 initial. Velocity 1 initial, velocity 2 initial. This is velocity 1 final, all right? Velocity 1 final, velocity 2 final. Just trying to label out what these V1s and V20s are. Initial, final, yeah. So that's how we can look at our momentum and collisions with a whole bunch of different equations. Now let's imagine the scenario where we might want to stop the ball, or say it's smashing into something. So here's a wall. Let's take this ball that was moving before, and let's just essentially just smash it into this wall. Alright? So previously it was moving with this M1, V1 sort of momentum, okay? And then then once it hits this wall, it's a sticky ball, right? Once it hits this, it's going to have a 0 velocity, 0 momentum. So it's just going to essentially stop. But it's going to require a certain force to stop that ball. Let's say it stops in about 0.1 seconds, okay? 0.1 seconds. I'm going to switch to color blue now, just to start keeping a little bit more track of this, because we're going to take a look at the force that is probably going to be the normal force that's going to stop this, but essentially there's a force that comes in the opposite direction that's going to transfer the force into this ball and stop it. So there's like a force that's going to slow this ball down in this 0.1 seconds in order to stop it, and in order to get that momentum to be 0. So there's this fancy little equation we can use. It's called an impulse. Impulse. That's essentially saying that this J, that's the impulse. Okay, this is the momentum. P is momentum, and J is impulse. That's going to be equal to the change of momentum. So notice how we had a momentum, we changed it, we slowed it down to 0. That's the changing of that momentum. We could represent that as the integral from the 0 to t, and we're going to look at that blue F right here. There's that force, and then that's just going to be the integral over time. The small, short period of time that we had there, that little force, that's what the impulse was that slowed this ball. Both of these are going to be in kg meters per second, which is the same thing as saying a Newton second. Okay, usually the impulses are going to be in Newton seconds, and the momentums are going to be in kg meters per second on that side. That's just the units of measurement that we use here. And so this is basically how impulse works with momentum. So impulse was just force times time. Force times time. And if that's the case, let's say we wanted to figure out what that force was. So we can say force equals, remember in a previous video I said that the force was the derivative of the momentum. So force is the derivative of the momentum. I'll make sure to link that in the description as well. We can essentially denotate that as the total net force is going to be equal to, let's divide both of these sides by time. So the change of momentum divided by time is equal to force. That's essentially saying that the dp over here, dp over dt, all right? Now this is the instantaneous situation, so that it's at that split second, if you wanted to calculate that. Or we could also even say that delta p over delta t, if you wanted to figure out what the average force was that was slowing this, this ball down, I suppose. And we can also say that's the m dv over dt. This is also, it's just if you happen to know velocity, and keeping in mind that momentum is simply velocity times mass there. So this is just a couple different ways that we can represent force in with these equations as it pertains to momentum. In the previous video, we had discovered that kinetic energy is simply the momentum over velocity of, the integral of momentum over velocity. That's what kinetic energy would be. If we were to calculate that out, we would actually get 1/2 mv squared. So that's quite interesting how kinetic energy relates to the momentum, and how the impulse is simply the integral of momentum, I guess, or the integral of force, the change of momentum, integral of force. Interesting. So now that all these things relate, we're going to be able to move into the next topics, which would be like angular momentum, and that's what's going to be coming up. So it's all these things in physics build off of each other. This is why we're going step by step here. Now hopefully you like these videos. If you do, make sure to like and subscribe, and go ahead and ask your questions in the comments if you have any. Thanks for watching.